Hey guys, in this video we're going to talk about some applications of exponential functions. In particular, we're going to look at earning money via compound interest. We're also going to talk about the number e in chapter 4, section 5. And so I want to start this lesson with a little quote that Albert Einstein supposedly said. He said, "Compound interest is the eighth wonder of the world. He who understands it earns it, and he who doesn't pays it." So what he's talking about is that exponential growth is very powerful, and we're going to see why. Okay, first of all, I want to do a little bit of a review. So recall that with exponential functions, we had the form y equals a times b to the x, where b was the growth rate and a was our initial value. Okay, so let's answer some of these questions just to refresh our brains on exponential growth. Let Q be the quantity. Q equals 148 times 1.137 to the t, which is changing over time. And the first question is, what is the quantity at time t equals 0? Well, we can look at it as either what's the initial value, or we can actually plug in t into this function. Let's plug in t equals 0 into the function, and what we get is the following. We get this guy. Now anything to the 0 power is simply 1, so this just becomes Q equals 148 times 1, which is 148. So that's our initial value, which you could have seen just from noticing that this was A and this was B. Okay, is the quantity increasing or decreasing over time? Well, that depends on if B is bigger than 1 or between 0 and 1. And B is larger than 1. So B is 1.137, which is bigger than 1, so this thing is increasing over time. The third part says, what is the percent unit time growth or decay rate? So when they're looking for the percent, they're asking for R. So remember, we had this formula for R. We had that B was going to either be 1 plus or minus R, depending if it was growth or decay. Since we're growing, it's going to be 1 plus R. So we have B is equal to 1 plus R. And it turns out that B is 1.137. So we have 1.137 is equal to 1 plus some number R. So what does this number have to be to make this equation true? Well, R has to be 0.137. If we want to write it as a percent, we have to move the decimal to the right 2 units. So R is going to be 13.7%. And that's our answer. So that was our little exponential functions review. So let's talk about why exponential growth is so powerful, especially when it comes to money. So here's a question that you should consider. Would you rather have $2 million? Or would you rather have a penny doubled every day for 30 days? All right. So think about that. Think about what, if you were on a game show and the host asked you this, what would you do? Well, let's see. On day 1, we have a penny. So we just have a penny, 1 cent. Now on day 2, if I double that penny from day 1, on day 2, I have 2 cents. Okay. On day 3, I have 4 cents. On day 4, I have 8 cents. And so forth. And the question is, what will I have on day 30? What will I have on day 30 if this pattern continues? Well, I can represent this situation with an exponential function, right? In this case, our initial value, our A, is going to be a penny, because that's what we start with. And our B, our growth rate, is going to be 1 plus R, the percent change. Now, what's the percent change? We can see, we can look at it in a couple of different ways, but we can see that R is changing by 100%, right? Because we're doubling. So this is from a penny to 2 pennies, that's 100% change. From 2 pennies to 4 pennies, again, that's 100% change, and so forth. We can also look at this in terms of B. So 0.01 times times what is 0.02? That has to be 2. 0.02 times 0.04, again, that's 2. So B has to be 2, is what I'm trying to say here. That's our growth rate. And we can actually write our amount of money that we're going to have with these two things. So we have the amount of money we're going to have on day T is going to be our initial value. So again, let me just write it like this. We have our initial value A times B. And usually we'll put to the X or to the T. But since I'm starting on day 1 instead of day 0, I'm going to put T minus 1 so that my equation makes sense. So if I put in, for instance, 1, for that indicates day 1, I get 0.01 times 2 to the 1 minus 1. 0.01 times 2 to the 0 is just 0.01 times 1, which is 0.01. So that checks out. Day 1 checks out with the 1 cents. If you put in 2 in for T, you're going to get 2 cents out, and so forth. So that's why we have to put the minus 1 in the exponent. But this is a function that represents the situation of the penny growing. And so the question is, what's the better deal? Do I double the penny every day for 30 days? Or do I take the $2 million? Let's find out. So when T is equal to 30, remember that's our days that have passed. What we get is A equals 0.01 times 2 to the 30 minus 1. So this is going to be 0.01 times 2 to the 29th. And when I put this in my calculator, I get, let's see, I get $5,368,709.12. So this is on day 30. So what's the better deal? You should double the penny for 30 days. This is much more than $2 million. So this is kind of cool, right? Because exponential growth is kind of defying our intuition. Like, you wouldn't think that doubling a penny every day for 30 days, you'll end up with over $5 million, but you do. So really cool stuff. And that's just one example of the power of compound growth or exponential growth. So let's talk about some terms that we're going to use here. The first one is interest, and that's just the cost of borrowing some amount of money over a certain amount of time. So if you buy a new car, you are given some kind of interest rate. Right now, they're pretty ridiculously high, to be honest, but basically you're paying a percentage of how much the car costs in order to, pay that amount over time. Like, you don't have to pay it all at once. The interest rate allows you to slowly pay off some kind of loan. And we're going to talk about two different types of interest. The first one is simple interest. And again, this is just the percentage of a loan. It doesn't change with time. So like car and home loans are examples. Your interest on your car is fixed. It doesn't change depending on what your balance is, like how much you've paid off the car. So simple interest is good when you're trying to pay off things. Compound interest, on the other hand, is a percentage of the loan and interest that it accrues every period. So it's basically interest upon interest. And compound interest, again, when you hear the word compound, you should think of exponential, right? These two ideas sort of go hand in hand. So if you think about how fast an exponential function grows, compound interest should scare you if you are in debt. So credit card companies use compounding to calculate your interest. And that's why some people get trapped in debt cycles, because compound interest, if you're not savvy with math, you can really get screwed by the credit card companies and by loan sharks. So we'll go into that. But yeah, so the two different types of interest are simple interest, doesn't change based on your balance, and compound interest. It does change based on your balance that you owe. So again, little side notes. I just want to give you guys some context about this, just in case you don't know about it. But compound interest is excellent for investing. That's the type of interest you want if you're trying to grow your money. One way to invest is certificates of deposit. I'm not sure what the interest rates are on those right now, but these, your money will grow based on compound interest. Also, trust funds and bonds are other investments that accrue compound interest. Now, compound interest is very bad when you're borrowing money, on the other hand. So, federal student loans are not compounded, I don't believe, but private student loans are not good at all. That means that the amount that you owe is going to change daily based on your balance, and it's just going to keep getting larger and larger and larger. Also, credit cards, we're going to do an example where we actually compute, how much you would owe on a credit card based on some interest rate. And these payday loans, this is the loan shark people, they usually have some crazy type of interest rate. But again, all three of these use compound interest. Okay, so let's take a look at the compound interest formula. This formula is going to tell you how much money you owe after a certain amount of time, or how much money you have in an account after a certain amount of time, depending on if you are paying off debt or if you're, maybe have your money in an account and it's growing. Okay, so this is our formula. A is equal to the amount that you have at the end of the day, the amount of money that you have. P is our principal, which means this is our initial, we could say it's the starting point, how much money we have to begin with, or how much money that we have to pay off. So this is our starting point money. The interest rate, I made a little note right here. It's sometimes called the yearly nominal interest rate, or the APR. So this is the percentage of the principal that you're going to be paying over some amount of days, weeks, years, whatever. N is going to be it's going to represent the number of times that interest is compounded every year. And we're going to do several examples where it's compounded daily, it's compounded weekly, it's compounded quarterly. What does that mean? We're going to find out in a few slides. And then T is going to be how long, you have to either pay off the money or how long you keep money in a savings account. So this is just the time that passes. Okay, so let's just get into it. Let's do some examples. First example is, what is the balance after 1 year if an account containing $9,400 earns 3% yearly nominal interest? And it says it's compounded A, annually, and then B, weekly, and then C, every minute. So we have to change N in each three of these cases. Now let's figure out what P, R, and T are going to be. Well, P is how much we start with, right, in our formula. That's our principal. So the amount we start with, it says it contains $9,400. So that's how much we're starting with, is $9,400. It says it earns 3% interest, so that's going to be our interest rate. And we want to write 3% as a decimal. So to do that, we move the decimal over 2 units to the left to go from percent to decimal. So we go 1, 2, and then fill in the gaps there. So 0.03 is going to be R. All right? That's our interest rate as a decimal. And then our T is going to be how much time we leave that money there. Well, it tells us in the first sentence, we want to know what the balance is after a year. That's what we want to know. So T is going to be 1 for 1 year. And these 3 things are going to be the same in each scenario. So let's write it for part B and C as well. Okay, so it's part B, part C. Okay. Now we need to figure out what N is. And that's all we need, because in each case, we're looking for A. We're looking for the final amount that we end up with after a year of compounding, or exponential growth. So what does annually mean? If I'm compounding annually, annual means yearly. So I'm compounding once a year in part A. So that means that N is going to be 1. That's the number of times we compound per year. So knowing all this stuff, we can just plug it into our formula that we see to the right, and we'll be able to find A very quickly. A is going to be equal to the principal times 1 plus 0.03 over 1, all raised to the N times T, which is just 1 times 1. Okay, so if we compute this, if I simplify it a little bit on the inside, well, this is just 1 plus 0.03, which is 1.03, raised to the first power. And I can put this in my calculator, and I am getting $9,682 is my ending balance after a year. Okay, so that was the first example. So what about the second example? Now we need to figure out what is the N in this case. Well, this time it says we're compounding weekly, and we're given a little hint that there's 52 weeks in a year. So every single week we compound, and I have to do that 52 times, right? Because N is the amount of times I compound in a single year. So in this case, N is 52. Pretty simple, right? So I just plug in all of my values here. So A is going to be P times 1 plus 0.03 divided by N is 52 this time, all raised to the 52 times 1, which is simply 52 in the exponent. All right, let's put this in the calculator and see what we get. Remember PEMDAS, I have to do everything on the inside first, so if it helps, you should write down all of these intermediate steps. So 0.03 divided by 52 is going to give us a weird number. But if I add 1 to that weird number, I'm getting about, well, I'll actually just write it all out. 1.000576923, and this is all raised to the 52 times 1, which is all raised to the 52 power. So if I raise this to the 52 power and multiply by 9400, again using PEMDAS, parentheses, exponents, then multiplication, I get $9,686.19. So that is going to be my ending balance if I compound every week. And you can see that this guy is actually a larger balance than if I'm just compounding once a year. So the more you compound, the better, the quicker your money will grow. Okay, let's take a look at this part C. What if we compound every minute? Well, again, P, the principal balance isn't changing, neither is the interest rate, neither is the time that we leave it in there. But here we're compounding every single minute. So how many times in a year is that? Well, they give us a hint again. They tell us there's 525,600 minutes. Sorry, the Rent song gets stuck in my head. I don't know if you guys know that one, but in this case, N, my point is that N is going to be 525,600. And now we can just plug everything into our formula. So again, principal is 9,400 times 1 plus interest rate divided by the number of times we compound. And this is all going to be raised to the 525,600 minutes times t. There we go. Okay, so let's go ahead and simplify inside. Now, this guy, I'm going to do that first, parentheses first. And PEMDAS says, in the parentheses, you better do that division first. Okay, so we got that. And we're going to raise this to the 525,600, multiply by 9,400, and we get a final balance of $9,686.27. So there's not too big of a difference from compounding weekly and every minute just in this particular case. Okay, so that was our first example. Cool stuff, right? Okay, let's go on and do another example. You invest $1,500 into an account that has an APR of 4.8%. Your investment is compounded quarterly. How much will you have after 3 years? What if you're compounding annually? So let's dissect this. What are they trying to tell us about what our variables are in our formula? See if you can figure it out. What is P? What is R? What is N? What is T? Well, and again, they're asking how much will you have. So at the end of the day, we're looking for A. That means, that rhymed. That's how much, I've had too much coffee today, you guys. I apologize for my antics. But anyway, that is what you're trying to find, the ending amount. Now, what is this 1,500? What letter does that represent? Well, that's our initial investment. That's how much we're putting into this account. So that's P. P is going to be 1,500. And they tell us the APR. So they tell us the interest rate is 4.8%. So that is my R. But remember, whenever you put this in the formula, don't forget this. Write this percent as a decimal first. And when we go from percents to decimal, we have to move the decimal to the left 2 units. 1, 2. So R is going to be 0.048. All right. Excellent. How much will we have after 3 years? That's how long we're leaving this in. So that is our time. So time is 3. All right. So then it says if it's compounded quarterly, and then we're going to answer the annual question. So quarterly, what does that mean? What does a quarter mean? Well, a quarter is a fourth of something. So if it's compounded quarterly, that means 4 times a year. So that's N equals 4. Okay? Now we plug in all of these values into our equation right here. So P is equal, whoops, dropping my pen. P is equal to 1,500. 1 plus R, which we found to be 0.048, divided by N, which is 4, all raised to the 4 times 3. Okay, so we can simplify this, and you can use the calculator on Desmos. Just make sure you put the appropriate amount of parentheses. So if I clean up the inside doing parentheses first, 0.048 divided by 4 plus 1, I'm going to get 1.012, all raised to the 4 times 3, which is 12. So PEMDAS says, hey, you better do this part first before you multiply. So 1.012 to the 12th times 1,500, that is going to give me, let me just double check my work here. Yeah, this is going to give me a final amount of $1,730.84. And this was if compounded quarterly. if compounded quarterly. Now, the second part of the question asks, what if we're compounding annually? Well, all we have to change is the n value. So the only thing we have to do is change the n. Annually, again, means once a year, so n is equal to 1. If we're compounding annually, we just plug in the same values, except this time n is equal to 1. So we have 1,500 times 1 plus the interest rate divided by 1, all raised to the 1 times 3. And let's see. So this is going to give us, let's see what I get here. So this is going to be 1.048 all raised to the 3. So doing the exponent first, 1.048 to the third, I get about 1.15 times 1,500. That's going to give us an amount of $1,726.53. So this is if we compound it annually. And as we expect, it is a smaller value than if we compound quarterly. Because remember, if we're dealing with the same values, the more you compound, the more your money will be worth at the end of the day. All right, so this makes sense. If we're only compounding once a year, we're going to have less than if we were to compound 4 times a year. Okay. All right, let's do an example with credit cards. So credit cards usually have crazy APRs, interest rates. They're usually really high. Sometimes credit cards will have specials where it's like 0% interest for a year or something, which is really awesome. But then you keep that credit card, and then after a year is up, the interest goes up to like 22% or something crazy like that. So be careful about that. Just a little side note. Okay, most credit cards compound daily. So that's one piece in our puzzle. You charge $1,500 to a credit card that has a 21% APR. Find the new amount you will owe after 30 days. So we need to figure out what all of our variables are here. Now, what am I trying to find? Like, what letter am I trying to find? It says find the new amount you will owe. So that's A. That's the amount. And remember, A can either be like an amount of debt, or it can be how much you're accruing, like in savings or something like that. So we're looking for A. What is P going to be in this instance? What is our initial amount? Well, our initial amount is our initial debt, basically, in this case, and that's $1,500. That's how much we're charging initially to this credit card. They tell us the APR. It's pretty straightforward. That's going to be our R. And remember, we don't want to put 21 in here. Don't do that. We want to change a percent to a decimal by moving the decimal 2 units to the left to get 0.21 for R. Excellent. What else are we missing here? We have P, R, N. What is N going to be? How many times a year are we compounding? Well, if we compound daily, every single day, this credit card balance is compounded. How many days are in a year? That's 365, right? So N is going to be 365. How many times in a year am I compounding? The first sentence says, hey, we compound daily. This amount is going to change every single day for the entire year. So that's 365. And finally, T. T is going to be the time that passes, and that's going to be, in our case, 30 days. Now, notice in the formula it says time in years. So how do we write 30 days in years? Well, we know that there's 30 days in there's 365 days in a year. And so to write 30 days in terms of years, we just have to write 30 out of 365. Okay? So those are my values, and let's plug in all of these values into our formula. So we're looking for A. We have A equals P times 1 plus r divided by n, all raised to the n times t. Now what's cool about this is we have fraction multiplication and the exponent. So these 365s are going to divide each other out. So let's rewrite this. We have 1500 times 1 plus 0.21 over 365, all raised to 30. Okay, let's do the math here. So 0.25 divided by 365 plus 1, all raised to 30, times 1500. I'm getting $1,531. 1,000. Let's see. Am I doing this right? Okay, I'm like double checking, and I think I put in the wrong R value right here. This is supposed to be 0.21. My bad, you guys. Let's do this again. Okay, 0.21 divided by 365 plus 1, all raised to 30, times 1,500, and I'm getting, okay, this looks better, $1,526.11. So this is how much money your credit card balance is going to go up after 30 days. So it's going to go up basically by $26 with this interest rate and this balance. Okay, so the next thing we're going to look at is the continuous compounding formula. So what does it mean to compound continuously? This means we're compounding infinitely many times over infinitely many small periods. Okay, and we'll talk more about this in Calc 1, but for now, all we're going to do is focus on the formula and see how continuous compounding is different from regular compounding. Okay, so we have some components of our formula. A lot of them are the same as the previous formula. So our amount A is our future value, P is our initial value, our principal, R is our interest rate like before, but we make it positive when we're talking about growth, and we make it negative when we're talking about decay. So that's the little difference there. And then time, again, is the same, how much time has passed since you've left your investment alone or since you started paying off a debt. Now, this guy right here, this E, is simply a number. So E is just a number like pi. And it's like pi in the sense that it's irrational. So its decimal expansion goes on forever and ever. And all calculators have an E button that you can use, including the Desmos calculator. And it turns out that, just like pi is approximately 3.14, E is approximately 2.718. Okay, so this is the number E. And, just to show you how it works on the calculator, if we have Desmos right here, we can multiply numbers by E. So if we just put in just E, regular E, with the ABC keyboard bottom left, and I type in E right here, it gives me that number. I can do things with E, just like I can do things with pi. I can add numbers to E. I can subtract anything that you want to do. Anything that you can do with a number, you can do with E. So that's part of our formula here. So let's just jump into it and do some examples. Now, anytime in your homework you see the word continuous compounding, you should use this formula. Okay, so that's the key word to look for. So let's do this example. From time t equals 0, with t in years, a $1,100 deposit in a bank account grows according to this formula right here. What is the balance after 60 years? So that's part A. We're first looking for capital B, the balance. And it says after 60 years, we wait for this money to grow. So T is going to be 60, right? That's our time. And we simply plug in 60 in for T to figure out what our balance is going to be with this continuous compounding formula that we're given. So we have 0.04 to the 60. And let's see. I'm going to just put this in Desmos to show you guys how we can do this. Let's see what we get here. So let's go ahead and put this in Desmos. And we're going to put 1100 and then keyboard E. And then I'm going to do the exponent, the little a to the b power. You can see that in the keyboard towards the left. And in parentheses, I'm going to put 0.04, then another parenthesis, 60. And I'm getting, let's see. Yeah, so I'm getting about $12,125.49. So that is my answer here. Okay, so that's how we do that. All right, let's look at part B here. When does the balance first go over 50,000? Okay, so what variables am I given here, and what am I looking for? Well, when they're asking when, that's a key indicator that you're looking for time. What is the time when the balance is 50,000? That's what we're interested in. So in Desmos, if we plug in all of that info into this calculator, what we have is 50,000 equals, well, actually, what we're trying to do is we're trying to see when does the function y equals 50,000 intersect with the function y equals 1100 e to the 0.04t. So we need to put both of these things in Desmos. So let's do that. And instead of t, I'm going to use x because that's what Desmos likes as our independent variable. And then let's just double check this. We're looking at 50,000. So we're looking to see when is it true that this function equals 50,000. So let's see. I'm zooming out, just pinching out. And I see this intersection right here. So I'm going to zoom into this intersection. Where is this value true? And if I click there, it looks to be about 95.4 years. That's my x value or my t value. So after 95.4 years, this thing is going to be $50,000. That's what the account balance is going to be. So when does it first go over 50,000? What we can say here is after 95.4 years. Okay, so that is my answer here. Let's do some more examples. Okay, so a radioactive substance decays at a continuous rate of 13% per year. So it's decaying at a continuous. Here's the key word, y'all. When you see continuous, you know that you're going to use that E formula. P equals E to the RT. Okay, so that's the key word here. We're going to use, A is equal to P E to the RT. Okay, continuous. And it says 60 milligrams of the substance is present in the year 2009. Well, it's another clue. Write a formula for the amount present t years after 2009. Well, in 2009, how much do we have? We have 60 milligrams, so that's our initial value. So P is equal to 60 milligrams. That's our initial value. And I know that I'm going to be using this formula right here. So the only other things that are missing, the only other thing is R. So what is R? Well, 13% as a decimal is 0.13. But remember, with continuous compounding, you want to make sure to attach a negative to it if it's decaying or shrinking. So I'm going to attach a negative here to it. Now, you don't do that in the other formulas. This is the only formula where, we attach a positive or a negative depending on if it's growing or decaying. Okay, so that's our P and our R, and now we have our formula. Our formula is simply 60, our initial value P, times e to the R, which is negative 0.13 T. So that is our answer here. And we leave T alone because that's our independent variable. That's what we're going to be plugging values into. Okay, so the next question says, how much will be present in the year 2023? Well, remember, T represents the years after 2009. So how many years after 2009 is 2023? That's going to be 14, right? So T is equal to 14 in this case. And all we do is plug that value into our function right here. So we have 60 e to the negative 0.13 times 14. And let's put this in the calculator. Or on Desmos if you like that. And let's see what I'm getting. I'm getting about 9.72. So A is equal to 9.72. And since I'm talking about an amount that was originally in milligrams, that's what my units are going to be here. Okay, so it says estimate when the quantity drops below 6 milligrams. So again, carrying this formula down, we have 60 e to the negative 0.13 times t. So that's our formula. And the question is, what's going in for our variables? Well, again, when it says when, that's a key that you're looking for t. It's a key word. So what is this going to be? Well, this has to be the amount that's present. So estimate, when the amount is 6 milligrams, what time does that occur? That's what you're trying to answer. What time is the amount 6 milligrams? So all we're going to do is plug in 6 for A and solve for T. Now, we don't have the tools to do that quite yet. We will next lecture. We're going to talk about logarithms. But what we can do is we can use the graph again with Desmos. So we can say, hey, when is it true that y equals 6 and 60e to the negative 0.13t intersect? When do these functions intersect? So let's see. And again, I'm using x instead of t just because that's what Desmos likes. And then, what was it? Y equals 6 milligrams, so y equals 6. So let's just pinch out of here and see what's going on. Okay, so I see the red line for y equals 6, and I just zoom in. And let's see what this is. So when I click that, on the function, we have 17.7. Okay, so the function is t equals, so we have t equals 27.7, but that's not quite our answer because this is years after 2009, right? Let's double check this. Sorry, not 27.7. Don't know where I got that from. 17.7. Let's put that back in. So t is equal to 17.7. And recall, this is the years after 2009. So just imagine yourself answering this question estimate when the quantity drops below 6 milligrams. You wouldn't tell someone 17.7 years. What does that mean? When? Compared to what, right? So how many years after 2009 is this? Well, what's 17 and 9 going to be? That's going to be 26.7, right? So this is approximately in 2027, right? If we add 2009 plus 17.7, that's approximately in the year 2027. So this is our answer right here. This is our answer. That's when the quantity starts to drop below 6 milligrams. Okay, let's work on another example. For the initial quantity Q naught equals 100 and the growth rate is 4% per unit time, give a formula for the quantity as a function of time and find the value of the quantity at time equals 0. So the first part says, and I encourage you to pause the video and see whether or not you can set this up. The first part says assume the growth rate is not continuous. So this time we're not using the E formula. We're actually going to be just using our basic exponential formula because they're not talking about compound interest here, compounding. You know, since those words were not brought up, we're going to use our original formula that we talked about in the very first exponential lecture. And that was this formula. Remember that? Here, A was the initial value, right? And B was the growth or decay rate. So this is the formula we're going to use for the first part, part A. So it tells us that our initial quantity is 100. That's Q of 0. Okay, that's in the first sentence. So that means that A, in this case, is going to be 100. And B is going to be, well, they tell us the percentage, and we need to change the percentage in terms of the value B, in terms of the growth rate, not the growth rate percentage. So remember that since B is going to be 1 plus R, since we're dealing with growth and not decay, and R is going to be 4%, because that's how much it's growing by. So this is going to be 1 plus 0.04, that's 4%, so B is equal to 1.04. Okay, so that's A and B. And our function is going to be 100, so that's A, times 1.04 to the T, because that's our independent variable here. So that's our answer for this guy. Now the second part is saying, hey, what's the value of this function when T equals 10? So all we have to do is plug in 10 into the function we just found. So Q of 10 is going to be 100 times 1.04 raised to the 10th power. Let's see what that gives us in the calculator. Times 100. Okay, so I am getting about 148.024 as my answer here. Okay, so that's part A. So that's when we assume it's not continuous. We just use our basic exponential function here, where A is at the initial value and B is the growth rate. Okay, so it says assume that the growth rate is continuous. So this is our formula. A is equal to P e to the RT. Okay, that's the formula we got to use now. So what is our initial value? Well, we're told that it's 100 in the first sentence. So in this case, P is equal to 100 because that represents our initial value. R is going to be our growth rate as a percentage, right? And so here we have basically, let's see, 4% growth. That's what they're telling us. And so this is just going to be r is equal to 0.04. And it's positive because we're growing. Okay, so that's our percentage growth rate. And that's it. T is our independent variable, so we leave it alone. E is a number. And so Q of T in this case is simply going to be P times e to the r t. Okay, so that's our answer there. Now let's do Q of 10. Now we're simply going to plug in 10 into the function. So we have 100 e to the 0.04 times 10. And what I'm getting here, and by the way, this is our first answer, is, let's see, put this in the calculator. I'm getting about 149.182 for our answer here. So as you can see, the growth is going to be greater in the continuous case versus the case that's not continuous. Okay, let's go ahead and do this last example. And I encourage you guys to try this one on your own. All right, so it says for the initial quantity Q naught equals 500 and the decay rate is 6%, give a formula as a function of time and find the value at time t equals 0. And actually, I think that's meant to say 10 because that's what we found here. Adjust your notes if you put t equals 0. This is supposed to be t equals 10. I apologize. Let's move on then. So this is t equals 10. Okay. Now we're going to do the same thing. We're going to assume that the decay rate is not continuous. And in that case, we use our function, actually we can just say y is equal to a times b to the t, or b to the x if you like that. And in this case, our initial value is what we started with, and that's 500, as you can see in the first sentence. Our b is going to be, this time it's going to be 1 minus our decay rate as a percentage. And r as a percentage, in this case 6%, is just 0.06. So our b is going to be 1 minus 0.06, which is going to give us 0.94. So b is equal to 0.94. Check, check. We got those two things. So now we can write our function. Our function is going to be Q of t equals a times b to the t. Instead of x, we're using t here. Okay? Now Q of 10, I'm just plugging in 10 into the function. So if I plug in 10 into this function for t, I get 0.94 to the 10. And let me just punch this in my calculator real quick and see what we get. So 0.94 to the 10 times 500. That's giving me 269.3. Write that a little bit better. 269.308. And that is my answer here for part A. So this was my function, and this was when I evaluate that function at 10. Okay, let's go on to part B. So now we're assuming that it's continuous, and again, that key word tells me that I need to use the formula A is equal to P e to the RT. Now, P is our initial value, and it's the same concept as before. It's going to be 500. Our R is going to be our decay rate, so it's going to be 0.06, but we're going to attach a negative to it because remember, with the continuous case, we attach a negative to our R. All right? And that's it. That's what we need for the formula. So Q of T in replacement of A is going to equal P times E, which is just a number, to the RT. And that is my function here. So that is this first part. Now the second part says, hey, plug in 10 in for t. So let's go ahead and do that. I have 500 times e to the negative 0.06 times 10. And when I punch this in the calculator, let's see what I get. Let's see. Okay. All right, so I am getting 274.406. And maybe it would be good to use units here. Well, I guess they didn't use units in the problem, so we don't need to. That's fine. But anyway, this is our answer. Thanks for watching, you guys. I hope this video was helpful. And I'll see you guys next time.